In this video, we'll be fleshing out our EFI bootloader to load our kernel into memory and then run its entry function. The entry function for the kernel at the moment is just this start function, and this is the result that we will get. Alright, to start off with this video, we're going to turn our template EFI application into a bootloader to load our kernel. But before we can do that, we need to actually make a kernel for our bootloader to load. So, open up your favorite code editor. I'm going to be using Visual Studio Code for this tutorial, and you want to do open folder. And then what you're going to want to do is do 2 backslashes WSL $ and then backslash, go into Ubuntu, or whichever WSL installation you have installed, home, your username, and the name of your operating system. Now, go into kernel, and then into source, and just select folder. Alright, we don't have any source at the moment, but we're going to change that right now. Create a new file, and call it kernel.c. So this will be the entry point for our kernel. Now, we can't actually write much kernel code at the moment because we don't have a bootloader to load the kernel to begin with. So, just to test that our bootloader is working, we're going to make the kernel return a value. So we'll do int start, and we want to return a value of, say, 1, 2, 3. Now we have a makeshift kernel that we can load with our bootloader. Now we're going to need to compile it, and we'll be compiling it into the ELF format. This way we can load it into memory using our bootloader and then run it. So to get started, we'll be editing the makefile that came with the template that was provided. So open up your file explorer and go to your workspace directory. Go into kernel and edit this makefile. Alright, now what we have here is we have the setup, build image, and run targets. Now you would have used these in episode 1 to set up and build the image to test the Hello World EFI application. Now we're going to need to add some more targets. We need to add a kernel target, so just do kernel and then a colon. And then we want to do $objs, which is for our objects. Now as you can see, the objects is a variable that contains all of the object files that we need to compile, and it finds these object files by looking for all of the .c source files in the source directory. Now this line here is a function that I've provided that will find all files with a specific extension, and that's what we're using to find all of our source files. Eventually we'll do this with .cpp as well if we want to do some C++ code, but for now we'll be doing it in C. For the objects target, we need to tell it how to actually compile the object. So, $bracket objdir, which is declared up here in the object directory equals lib /%.o. And now we need $bracket source directory, so srcdir for source directory, /%.c, and that is telling the makefile how to compile all of our .c files in our source directory into .o files in our object directory. Now this is just my preference, but I like to echo, so we'll do an @ to hide the actual echo command, but we'll echo exclamation mark, a couple equal signs, compiling, $up arrow. And what this will do is just, it'll echo in the terminal all of the files that we're compiling. Now, we'll do another @ and make directory. Now this is just making sure that all of our source directories are copied over into our object directories so that no errors occur when compiling. So we'll just make directory -p $bracket @d. So this is basically just making a directory in the objects directory for every directory in source directory. Now we need to actually compile it. So $bracket cc, which is for our compiler, which is defined up here. Now this shouldn't be min.gw, this should be just standard gcc. That's something that I forgot to change, just make sure you change that. Now we need $bracket c flags, and that will just put all of our C flags, which are just these ones here, on the end of our compiling command, -c, $up -o $at. Now what this is doing is setting the input file to be this one and the output file to be this one. So all of the source will be compiled into all of the objects. Very good. Now, after all of our compiling is done, we need to link it. So we'll create a new target called link, and just like with compiling, we'll also echo linking. And then we'll do $LD. Now our LD directory hasn't been declared, but LD equals LD. So $brackets LD space $LD flags. Now we can define our output, which will be $build directory, which is defined up here just in bin, which stands for binary, /kernel .elf. And for our linker to be actually able to find all of our objects, we just need to do $bracket objects bracket. And that'll just put all of the array of objects into this command line. Right, we're almost done with this. Now we just need to declare our linker script. We don't have a linker script at the moment, so what we're going to need to do is create one. Let's create a new text document, call it kernel.ld, and we'll edit that one as well. Alright, now the first line we need to do is make sure that the output format is correct. So our output format for our linker needs to be ELF 64-x86_64. Now this is just telling our linker to produce an ELF file, which is what we need. Now we need to define the entry of our kernel, which is _start. Now we just need to define some sections. Now for anyone who followed the other operating system tutorial, these sections are exactly the same as the previous linker. But for anyone who hasn't followed the old one, we'll go through that now. So, .text, :align, bracket 0x1000. We'll make a bracket block and asterisk bracket dot text bracket. So we're defining a text section and putting all of the text sections of our code into this text section. Now, similarly to text, we need data, so we can just copy that and replace text with data. Then we can replace text with RO data, which stands for read-only data. And we need one more, which is .bss. Now BSS is uninitialized data. So along with asterisk .bss, we need asterisk common. Alright, and that's our linker script complete. Now back in our makefile, we need to set the linker script variable to be kernel.ld. Now we should be able to run the kernel target and it will produce a executable for us. So we'll open up our terminal and cd into our workspace directory. Then we'll cd into kernel and then we'll do make kernel. As you see, I've made a mistake. So kernel needs to create the objects and then it needs to link. So we'll do create objects and then link. So we'll just try that again, make kernel, and now it's linked. But our target ELF64 x86-64 not found. And that's because this needs to be a dash and not an underscore. We'll try that one last time and it has successfully linked our kernel.elf. Now we'll go back into our workspace, into kernel directory, and then go into bin, and we have kernel.elf. We have successfully made a kernel as an ELF file. Right. Now there's one last thing we need to do before we leave this makefile. We need to copy the kernel ELF file into our image so that it can be run. So what we can do is just copy this mcopy line, and what we need to do is $bracket build directory, because that's where kernel ELF is placed, /kernel.elf, and that should be right. Now if we do make build image, we don't get an error. Now we're not able to test this at the moment because if we try and look inside the image, well, Windows will give us an error, but we'll just need to trust that it's in there. Now we can head back over to our EFI application and start building it into a bootloader. So in your favorite code editor, we can go up to File and do Open Folder. Now we'll go back into our workspace of our operating system and go into GNU-EFI, into Bootloader, and do Select Folder. Alright, now this is our Hello World application that we have started with. We can just go ahead and get rid of all of this because we no longer need it. Before we get into loading the ELF file, we're just going to do initialize lib and give it the image handle and the system table. Now what initialize lib does is it just sets up the UEFI environment to be able to use special commands that will make our life easier. Now before, we had to use system table console out to print something to the screen, but now we can simply just use print L to make a long char and some sort of string. So we'll do like string blah blah blah, and then we'll do our return character \n\r, so next line and then return. And this will print string blah 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 to the screen. And it's a lot easier than how we were doing it before. Now just to test that, we can cd into our GNU-EFI directory. So from kernel, we just do /GNU-EFI and do make bootloader. I just realized I did return status, but we don't have status, so we can just do return EFI _ success. And that should work just fine. So we'll make bootloader, and then we can cd back into our kernel directory and do make build image, and then running that, we should be able to see our new string. And as you can see, we can see our new string. So that makes our life a lot easier. And this print function also allows for string formatting, which will make everything a lot easier, at least until we leave the UEFI boot services, in which case it's going to get a lot harder from then on out. Alright, so let's start making our bootloader. We're going to make a function to be able to load a file from the file system. UEFI gives us a few handy functions to be able to do this, but I like to just wrap it all into one neat function. So we'll do EFI _ file pointer load file, and we're going to need to pass it a few parameters. So we'll do EFI _ file directory, and this needs to be a pointer. So UEFI treats directories as files. So if you want to get a file that's nested inside of a directory, you need to pass it this directory first. Alright, then we want char16 pointer path, and this is just our array of characters that defines the system path that the UEFI is going to look for our file. And then we just need EFI _ handle image handle and EFI system table pointer system table. Now basically every UEFI function needs either the image handle or the system table, so we're going to need to pass them to pretty much every function or store them globally. It's really up to you. Alright, so we'll declare a EFI file pointer loaded file, but we'll just leave that uninitialized at the moment. So our kernel ELF will be stored on the same file system that the computer boots from. If it's not on the same file system, then something has gone terribly wrong. So we need to tell UEFI that we are using the file system that we are booted from. So to do this, we just need to get the loaded image. So we'll just do EFI loaded _ image _ protocol. This is a pointer, and we'll just call this loaded image. And now we will do system table boot services handle protocol bracket, and we need to pass it the image handle Then we need a reference to UEFI loaded image protocol GUID. Then we need a bracket void pointer, and then a reference to our loaded image. Right, this will give us the EFI loaded image protocol. Now we need to get the file system. So the EFI underscore simple file system protocol pointer file system. And then similarly with this handle protocol up here, we need to do another handle protocol loaded image device handle. And we need a reference to GEFI simple file system protocol GUID. And just like before, we need a void pointer to file system. And this will give us the file system that we've booted from. Right, now we need to check if directory equals null. So if directory equals null, file system open volume file system and a reference to directory. So this is just checking if the directory is null, and if it is null, then we're setting the directory to the root of our file system. Right, now we need to do EFI underscore status s equals directory open directory, a reference to loaded file, path, EFI file mode read, EFI file read only. So this is just basically opening the directory and saving the file into loaded file, which we declared up here. So now we need to check if this succeeded or not. So if s, which is our EFI status, so if s does not equal EFI success, we need to return null because we didn't end up getting a file. But if we did get a file, then we can just return loaded file. Alright, now we can just check if this load file is working by doing if load file null, because we want the base directory, the root directory of our file system. Now we need the path, which is a long char, and we'll call it kernel.elf. Now we just need to give it the image handle and the system table. So if our loaded file equals null, we need to print could not load kernel. But if it doesn't equal null, then it's loaded correctly. So we can do kernel loaded successfully. Now we can just test this and see if we've done everything right. So we'll go back into our terminal and cd back into GNU EFI and do make bootloader. Alright, file system is used uninitialized in its function. Now I just need to get a reference to file system, and that is where my error was. So we'll try that again, and everything has worked properly. So now we can cd back into kernel and do make build image. And now we can run that. And if everything worked properly, it should say kernel loaded successfully. And as you can see, it says kernel loaded successfully. Now if we change this path to something random like that, and then try and do that, it will not work. So just as a sanity test, we can now run that once again with the bogus path, and as you can see, it now says could not load kernel. So we've successfully found the kernel file within our image. Now that we have this file, we need to actually do something with it. Before I forget, before we continue, we should just change that random thing back to kernel.elf. Now the next thing we need to do is get the ELF header so that we can get some information about the file. So we'll go to the top of our bootloader and we'll do include elf.h, and we'll just use these arrow brackets. Now we'll go back down to our EFI main function, and we can define a elf64 underscore ehdr, which is our elf64e header. And we'll just call this header. We'll do a couple of brackets just to signify that we're defining what this header is. Now we need uint n file info size. Now we need to get the EFI underscore file info pointer file info. We'll just declare that pointer so that we can get the file info from this file. So before we continue, we need to actually save our loaded file into a variable. So EFI underscore file pointer kernel equals this value here. So kernel equals load file. And now we can just check if kernel equals null. So right, back down here, we can now do kernel get info kernel, get a reference to g EFI file info GUID, a reference to file info size, and null. What this will do is set the file info size to the size that we need for this kernel. Right, now we need to do system table boot services allocate pool. Now what the allocate pool does is essentially the same as malloc. It just allocates some memory for us to use. So allocate pool EFI loader data file info size void pointer reference to file info. And this will just give us a pool of memory the size of file info size. Now we need to get the file info. So kernel get info kernel reference to GEFI file info GUID, a reference to file info size, and now we need void pointer and a reference to file info, just like what we had in the allocate pool function. Alright, now we need a uint n size equals size of header kernel read. And this read function just actually reads the bytes from the hard drive. So this load file doesn't actually read the file contents, but this function here will read the file contents. So that's what we need. So we need to read kernel, a reference to size, and a reference to header. So that'll just read the amount of bytes that's in size into the header. Now we need to see if the ELF file is actually an executable ELF file and all of the other header values are correct. So to do this, we need a memCompare function. Right, so we'll need to do int memcmp, which is memCompare, memory compare, const void pointer a pointer, and we need const void pointer b pointer, and we need a size t of n. Now we need a constant unsigned char pointer a equals a pointer and b equals b pointer. Now for size t I equals 0, I is less than n, I plus plus. So basically we're scanning through two buffers of memory and we're scanning for the size of n. If a indexed by I, so that's just basically a plus I times size t, if that is less than b I, we can return -1. Else, if a indexed by I is greater than b indexed by I, we can return 1. And on the outside of this for loop, we just need to return 0. So that's our memCompare function there. So we'll go back down to the bottom of our EFI main function. And now we need to do quite a few checks. So the first one we need to do, if and I'll put it on separate lines just to make it a little bit neater. So if mem compare the reference to our header.e underscore ident for our identity, ei underscore mag 0, and this is just all sort of ELF stuff. If you're interested in how this is sort of correlating to separate things, you could look up the ELF file specification, but I'm not going to go terribly in depth. So we'll compare ELF mag and self mag. So if it does not equal 0, or header.e underscore ident indexed by ei underscore class does not equal ELF class 64, or header.e underscore ident indexed by ei underscore data does not equal ELF data to LSB, or header.e underscore type does not equal ET underscore exec for executable, or header.e underscore machine does not equal EM underscore x86 underscore 64, or, and this is the last one, header.e underscore version does not equal EV underscore current. So if any of these are not correct, then we need to print kernel format is bad. Else, if it is good, we can print kernel header successfully verified. Alright, now we can test that out and see how that goes. Now, one thing I forgot to do is we need to go back into the makefile of our kernel. So that's in kernel and then makefile, so we'll edit this one. And we need to change this LD flag from shared to static. Alright, now we should be able to compile all that and see if it works. Alright, now we'll need to cd into our workspace, cd into kernel. Now we can do not cd into kernel, so we need to cd into GNU EFI and do make bootloader. And now we have a few errors. So mem compare needs to be const void and not vonst void. Try that again. Now size t is an unknown type name, so we just need to define that. So we'll do type def unsigned long size t. Alright, we also need a pointer before b, just an asterisk before b. Alright, now the bootloader has been made, we can cd back into kernel. We need to make kernel, and now we need to do make build image. Now, as you can see, our kernel is loaded successfully and the kernel header is successfully verified. Alright, so we've loaded the file with load file, and then we've created the ELF header, we've allocated some memory for it, we've filled it with the kernel header information, and then we've checked the kernel header against some constants to see if everything is as we need it to be. Now, using the information from the header, we need to actually load the program information from the ELF file into memory. We'll create a struct ELF64 underscore PHDR, which is ELF64 program header. This is a pointer, and we'll call it pheaders. We'll do curly brackets just for neatness, and we'll do kernel set position. And what this does is just sets the offset in bytes of the file when we read it. So kernel and then header.e underscore ph offset. So that's just the program header offset. So now the next call we do to kernel read, it will start at the program header offset. Now we need a uint n size equals header.p e underscore ph num, which is our program header num, times by header.e underscore ph ent size, which is program header entry size, I believe. Now we need to allocate some memory for the program headers, so we'll do system table boot services allocate pool EFI loader data, size, void pointer reference to program headers. Now, finally, we just do kernel read, which will just get all of the bytes of the program headers and put it into the struct. Kernel, reference to size and program headers. Alright, so this has now become an array of program headers. So it's still a pointer to the first program header, but we will be able to iterate through them. Now we need to go through all of these headers and actually load the binary information. So we need a for loop, so for, and this is going to be quite large. So for ELF 64 underscore P header, pointer P header equals P headers, which is the one that we just declared up here. Now we need bracket char pointer P header less than bracket char pointer P headers plus header dot e underscore program header num times header dot e underscore program header entry size. So we'll start off with a reference to the first program header, and while the program header address is less than all of the program headers, we will continue. So program header equals cast to ELF 64 underscore P header pointer 2 brackets char pointer PHDR plus header dot e underscore ph entry size. Right, now we can actually get to the body of this for loop. So we need a switch. So we need the switch of the P header, P underscore type. And in the case that the type is PT underscore load, we're going to need to allocate some pages so we can actually load the program into the memory where it has to be. So int pages equals bracket P header P underscore memsz plus 0x1000 minus 1 and bracket divide by 0x1000. So basically what we're doing is just getting the memory size and then rounding it up so that we have enough memory to contain it all. Now we need to do ELF 64 underscore ADDR for address segment equals P header P address. So P underscore PADDR. Now we need to allocate some pages, so system table boot services, allocate pages, allocate address. Might help if I spelled allocate correctly. So allocate address, EFI loader data, pages, and a reference to segment. Now we can do kernel set position, kernel P header P offset. So we're just setting the correct offset to read from the kernel, and now we need to do int uint n size equals P header P underscore file sc file size, and now we can do kernel read kernel reference to size void pointer segment, and now we can do break. Now at the end of this we can just do a sanity check, so we'll do a print kernel loaded, and we'll run this, and if it doesn't print kernel loaded then we've done something wrong and it's crashed. So inside the GNU EFI directory we'll do make bootloader, and we have a little bit of mistakes. We just need a bracket after case pt load and a closing bracket after break. Now running make bootloader again, it will complete successfully. Now we'll cd back into kernel and do make build image. We haven't changed kernel at all, so we don't need to rebuild kernel. Alright, now running it, we should hopefully get printed kernel loaded. And here we are. It printed kernel loaded, but it got covered up by the UEFI shell text because we didn't do a return character, but that's okay. It's worked successfully. We'll just add those return characters now. Alright, now the kernel's been loaded, there is only one thing left to do, and that is to call the entry of the kernel. So that will be calling this here, this int start function. Alright, so to do a call to our function, we're going to need to create a function pointer. Now our kernel start function returns an integer at the moment just for testing, so we're going to create an integer function pointer. So we need to do int bracket pointer kernel start, closing bracket, and then 2 empty brackets. Now if we were passing anything to the kernel, such as memory map information or graphics information, we would put it into this parentheses here, but we're not giving it any information at the moment, so that's just empty. So that equals 2 brackets, 2 underscores, attribute, 2 brackets, sys v underscore abi, get out of those 2 brackets there, int bracket pointer, closing bracket, and then 2 empty brackets, get out of 1 more bracket, and now do header.e underscore entry, and then close the last bracket. So basically what we're doing is defining a integer function pointer at the address of header.e entry, and we're giving it this attribute. Now what this attribute does is just basically tells the compiler to use the correct calling conventions for the function so that nothing goes wrong. We can call the function and then return to this point. Now eventually we're not going to be returning to this point because we won't have any use for the UEFI boot services, but for the moment being we will be returning. So now to get the result out of our kernel and to print that on screen, we just need to do print L, and we'll do a %d, which is the formatting code for a decimal, and our return characters, and then we'll give it kernel start and brackets. So basically what we're doing is making a string with a formatting code of decimal, which will be filled by kernel start, and kernel start is returning this value that we have here. Now we can rebuild our bootloader. So we'll do make bootloader. I misspelled e entry, it needs to be lowercase. So we'll try that again. Now we'll do cd back into our kernel directory, make build image. We don't need to remake the kernel at the moment because we didn't change it. We just need to build the image. And now we can run it. And as you can see, we have successfully returned 123 from our kernel. Now this is the first step into creating our bootloader. In the next video, we will be giving our kernel some important information about memory and some fonts so that our kernel can do some text drawing and several other important things that our kernel needs. But for now, that is a good starting point for our UEFI bootloader as we can successfully load our kernel file. That will be it for this video. As always, thank you for watching and I will see you next time.